our signaling part of the this class. Now, this is going to be a relatively short session. We'll be finishing up in about 20 minutes maybe. And then we're going to be off until the look like January 7, Wednesday, 7 January. But I'd like to at least get started on talking about signaling and just some fundamentals. The areas we're going to go over are shown up here. We're going to look at the industry overview, and then from there we'll first like to take a look at it, just kind of some basics of radio and mobile telephony. Then we'll look at the industry as a whole, and then we'll look at identities and architecture and generations. Now, I think I've told you this. I don't know if we mentioned it the other day. I've got two screens here, so I have the screen with the slides is right in front of me. That's where the camera is at, and the other one's over here. So I'm going to open up a chat window here in case you have any questions. I'll kind of glance at this chat. Or if you do have any questions, please just either write it in the chat window or stop me, and we'll answer any questions. So let's take a look at what we're going to do here. First of all, we're going to look at these areas. We'll look at mobile telecom basics, just some of the basic principles, the terms, and just kind of an overview of the industry. It's important to understand the different identities in a network. You have more than just your phone number. There's a lot of identities that are needed to make roaming work, to make call delivery work, different identities that you are known by, to page you, to bill you. So again, there's a lot of different identities. And we'll take a look at the generations. It's important to at least understand what is a second generation system and how does it communicate? What is a third generation? When did it come about? Why did it come about? What is the fourth generation? Why? What happened in 4G? What makes that unique to 3G? Why go to another generation at all? And now we're into an area or an era, I should say, with a fifth generation. So why all of these every 10 years a new generation? And we'll talk more about that and look at the motivations. And then just as equally important would be the signaling protocols. There's different protocols that are used in different generations. There's different protocols used for different purposes, some for communicating or transporting data, some of them for transporting voice over IP, let's say, some of them for more circuit related. And again, we'll define those terms, but these are the main areas that we're going to be looking at in the next couple months. So yeah, this is the mobile phone. Not that long ago, it wasn't all that many years ago. Back in the late 1980s, even into the early 1990s, it was basically a device for voice. It was a convenience. I remember when I first got my mobile phone back in 1988. It was amazing that you could actually move around and talk on the phone and drive in your car and talk on the phone. That was a big deal. Today we've got things like long battery life, which was never available back then. Performance and graphics and picture taking and sound and the speeds are incredible. So it's just a kind of an amazing device. So a couple things about it. How does it work? How does it know where you're at? How does it know what services you have? If you get on an airplane and fly to Dublin, Ireland, how does it know that you have any restrictions on your phone or what services you have? How do people find you? If they send you a short message, how does it know exactly where you're at? And how does it know when you are roaming on another network? If you're in your home network, you're using the cell towers, you're using all the facilities in that network. But if you roam into another network, you're using their facilities, but you still have to communicate back to the home, and the home network still has to talk to that visited network. So these are the areas that we're going to look at. Before we do, though, let's give credit to kind of the pioneers. There's many of them, but I think four of them are particularly kind of important in terms of wireless. The first one back in the 1800s was a guy named James Clerk Maxwell. He theorized, and he mathematically theorized that there were electromagnetic waves out there. That quite a few years later, it was demonstrated by a guy named Hertz. In fact, so much so that he gets credit for the wavelengths. Waves are in hertz. That's how you measure the different wavelengths. And a wavelength just being, think of it like a sine wave or any kind of wave. So he first demonstrated that there were electromechanical waves. So he gets a lot of credit. But the one that kind of practically showed that this would work was a guy named Marconi, and he developed he developed the antenna and proved that electromagnetic waves could travel. And he did that way back in 1901. He transmitted from Cornwall, England, to St. John's, Newfoundland, across the northern part of the Atlantic Ocean. He proved that a transmitted letter could be picked up across the ocean. He sent the letter S, which is just dot, dot, dot in Morse code. It's still kind of disputed whether he really heard that or whether he was just hearing static. He might have just been hearing static because it was done during the day, and typically waves don't travel much, amplitude modulated waves don't travel too much during the day. So he might have only heard static, but he does get credit for demonstrating that electromagnetic waves could travel. And the other one is a guy named Edwin Howard Armstrong. He was an American in New York City, and he developed FM, frequency modulation, which is what really made mobile communications work up until the digital age. These were frequency modulated signals. We use that today, of course, on radios. Prior to that, it was amplitude modulated. So he gets credit for FM. So these are kind of the four pioneers. When you look at electromagnetic waves, it's important to look at the spectrum and see at least where mobile telephony fits in. Well, if you look at the top part here, you have from 3 hertz. Now, a hertz being just how many of these cycles per second. So if you just think of like a wave going up and down and the distance between the 2 crests, how many of those can travel in 1 second? Well, the lowest end here is 3 of these waves in a second. And it goes all the way up into 10 to the 25 hertz. Well, that would be just incredibly fast. So the radio spectrum is in here. Then you have infrared, visible light, and ultraviolet, X-ray, gamma, and then cosmic rays. Well, what we're interested here for telecommunications radio is the radio waves, which is further broken up into these bands. So you have the extra low frequency, the super low frequency, ultra low frequency, and I listed down here some of the uses of them. The lower the frequency, the further it can go before the signal kind of dies out. Also, the lower the frequency, the more it follows the curvature of the Earth. The higher the frequency, the radio waves take on more the characteristics of light. It beams more, and the signal dies off much quicker. So that's just kind of a general characteristics of light. So if you look down here, things like amateur radios in this low frequency from 30, this 3,000 hertz, that's kilohertz being hundreds of hertz, and megahertz being millions of hertz. So AM radio fits into this. So AM radio is like 560 kilohertz up to, 1,500 kilohertz, somewhere in there. FM radio is up here in the VHF band. And this band, which starts at 3,000 million hertz up to, 300 million hertz up to 3,000 million hertz, which is at 3 gigahertz right there. That's really a very, very desirable band. Radio waves behave very well there. You can go through walls, you can go through windows. You don't need line of sight for cell towers. It's a very, very desirable band, but it's used for a lot of things. So it's used for TV and microwave and radio astronomy and radios and public land mobile. So this is where all the attention is as far as mobile telephony. The early mobile telephony in Europe was like in the 8 to 900 megahertz. In the United States, it was 824 to 896 megahertz. It was in that 800 megahertz range. Beyond that, these don't get real desirable. Now, there is some interest in this extra high frequency today for 5G. If you have extra high frequency, you can get very, very, very high speeds. I mean, like you can download a video very, very rapidly. The problem is you need cell towers everywhere because you don't have you have to have line of sight of that cell tower because again, the higher the frequency, the more the signal dies down very quickly and the more it takes on the characteristics of light. So this is just a frequency band. That's kind of a desirable. It's called the UHF, the ultra high frequency in the radio band. Just some general properties about radio. First of all, there's reflection, and that's good. If radio waves didn't reflect, you would need line of sight. You'd have to have cell towers everywhere. Well, if you look out the window or drive down the street, you don't see cell towers everywhere, because it relies on this reflection. So it's a change of direction when a radio wave bounces off of an object. The higher frequencies are more sensitive. So the higher the frequency is, the more sensitive it is to it hits a building or it hits a brick wall and it can bounce. So the higher the frequency is more sensitive to that. Attenuation is another characteristic. Attenuation is the loss of signal strength as it travels through a medium. You're going to lose some signal strength. You're inside of a building now. You're going to lose some signal strength as it goes through that wall. If it was a real high frequency, it wouldn't have that ability. If it was a real low frequency, it could go right through that wall. But you're going to lose some of that strength. Higher frequencies, like we just mentioned, higher frequencies lose their attenuation. They lose their power. In other words, when they transmit a power, the higher the frequency, the quicker it dies down. It doesn't go as far. Propagation is just some of the behavior that radio waves do travel at the speed of light. They do not require a medium, of course, to transport. They're just using the ether, the air, the atmosphere. And they undergo interference, and sometimes they do, again, change course. Another thing is refraction. Now, refraction is the change of direction of a wave passing from one medium to another. You can visibly see that if you put a straw in a glass or a pencil in a glass. It looks like it's bent there. Well, it's not. It's just a change of the medium. Now, this is when you think of wavelength, and so we think of these frequencies back here, all of these frequencies here, kind of imagine this right here. So this is the distance from crest to crest. You got these radio waves going like this, and the distance from crest to crest is called the wavelength. And how many of those you have at any one of these frequencies, again, the higher the frequency, the closer those waves are together. So if you look at in cellular telephony, right around 9, let's say frequency is 9,000. I'm going to go back to here. Let's say we're at the 900 megahertz. Okay, that's 900 million cycles per second. So if I divide that 900 hertz per second and divide that by the velocity, which is the speed of light, you get roughly the wavelength. And that's roughly a third of a meter. So the distance and when you talk on your mobile phone, if you're in the 900 megahertz range, which again, many of them are, the wavelength is roughly a third of a meter, about roughly, I don't know, about that much. That's how that wavelength is. The higher the frequency, the more those are going to go together. Again, nothing we're going to go any deeper than this on. Just be aware of this as you're talking on the mobile phone. These are radio waves out there, roughly at the 800 to 900 megahertz range. Early mobile telephony, basically, and this is going back, this mobile telephony can go back in some areas back to the 1930s, 1940s, even into the 1950s. There wasn't a lot. These were more like just two-way radios. So it was more of a two-way radio than an actual phone. And there were several here in the United States, they were called RCCs, or radio common carriers. Now they could have been called anything in other areas of the world. But what would happen is they would have a license. This company, this radio common carrier would have a license for, let's say, 10 channels. So it would place an antenna at a very strategically high place, and then it would offer these 10 channels. Well, if someone used one of the channels, you had 9 left. Then you had 8 left of the second person. And by the time you get into the 10th person, if the 11th person wanted to use the phone, sorry, you're blocked. You also could not access the network. You could not access another wireline network. Let's say your friend at home, you couldn't access that directly. You had to go through an operator. So there were very few channels with an antenna that was strategically placed at a high point. And once all channels were occupied, that's it. You had to wait for one of them to become available. And you needed operator assistance always to connect to the landline. So this was the whole idea of mobile telephony. You get just a certain amount of channels. You got this strategically placed antenna, and let's say in a tall building or somewhere, and that's it. You only had maybe 10, 15 channels. Now, obviously, as time went on, it was not going to be too adequate. You need more and more and more people. So you need to increase that capacity. So how do you increase in capacity? How do you increase your capacity? There's 3 ways you can do that. You can get more frequency. One way to do it. Now, in order to talk, you need a certain amount of frequency. It's not just one frequency. You might need 10 kilohertz of frequency, or 20 kilohertz, or 30 kilohertz. You need a band for your voice to actually go on there. You also need 2 bands if someone's going to talk back to you. Otherwise, it's like a walkie-talkie. Hi, Ralph, how are you today? Over. Ralph says, "Oh, I'm doing fine today, Steve." Over, and then we kind of share that same frequency. Well, again, that's not real practical either. So you can get more frequency, but in order to get more frequencies, you need to go to the government agency that controls that. And if you look at what's occupying this, there's no idle frequency here. In fact, quite the opposite. A lot of things use that frequency. And you generally, almost every nation, if not every nation, you need permission from the government. Okay, this is you have to have permission to operate at that certain frequency. If you operated at that frequency and a pipeline company did the same frequency, we'd interfere with each other. So the governments control what frequencies you have. So that's one way you can do it, and not a real likely way to do that. Again, there's no free frequency there. And remember, 800 megahertz, 900, up to maybe 2000 megahertz, that's a real desirable frequency band. So you might get freer frequency, or you might be able to get frequency at a higher band. But again, for mobile telephony, the higher it goes, the more cell towers you would need. The other way you can increase is improve your modulation. And there's different techniques to modulate. Modulation is what you're doing on the air interface. It's how your voice is now being converted over as you talk analog, how it's being converted over so it can be used on the air interface. Up until 1990s, this was analog. So it was just like a frequency modulated FM radio. Starting in the 1990s and now even through today, it's digital. So I'm talking analog, and from this microphone on, it's digital, digital, digital until it gets to your ear, and your ear then it's converted back to analog again. But a technique to increase capacity is to make that a digital signal. That's the second way. But that's not the key way. The key way you're going to increase capacity, because more and more people want to use this, is you radiate less power and you reuse your frequency at some distance away. So if you radiate power here at this cell, and you draw these cells as hexagons. Now that's how they're drawn. We know radio waves don't follow that little neat 6-sided hexagon. But again, it's a convenient way to draw it. Well, if you emit radio, let's say right here, but you don't blast it out. In other words, you kind of decrease the power, so it's only valid in this area. You can reuse that frequency some distance away. So this guy talking here can be using the exact same frequency as you're using here. because you're not bleeding over into here. So that's the whole idea of cellular. Cellular means that you can reuse frequencies at some distance away. Now, obviously, you can't overpower this. You can't blast thousands of watts of power so you'd bleed over to here. But if you just kind of, it'd be like me whispering. If I can whisper here, we can say the exact same thing at some distance away, and no one will hear me because again, you're whispering. That's the whole idea. So you want to use low-powered transceivers, which are transmitters and receivers, in smaller areas. And these areas are called cells. Now, how big are these cells? It depends. If you have cells in let's say an area like a shopping mall or something where people are walking, they can be very small cells. They can be a few meters, if you're or maybe 10, 20 meters in diameter. But if you're driving along a major motorway where the cars are going 80 kilometers, well, the cells have to be quite large. They have to be maybe several kilometers in diameter, maybe 5, 10 kilometers in diameter. So the cells are going to vary. They're going to vary in size, and they're not all the same size. But the whole idea of cellular is to reuse frequencies at a distance. And theoretically, if you kept shrinking those cells down, you could get more and more capacity. If I just keep shrinking, if I just keep powering less and less and less here, I can reuse frequencies at a shorter distance. But again, there's a practical limitation. If you're driving on a major motorway in the country outside of a city, and you're driving along at 80 kilometers, you can't have a cell that's only a few meters wide. That it couldn't keep up with you. It's got to be. It really depends. So these cells can vary, and you can only shrink them so much. Again, depending on the geography. So that was the real breakthrough. I think this is where we will probably call it a year now. We'll call it a 2025 and pick this up again in January. But this is where we'll pick it up. We'll talk about cellular communications, and we'll talk about, when we pick this up, we'll talk about the cells, how frequencies are reused, how you hand over from one cell to another cell, and how you hand over from one cell to another cell in two different systems called inter-system handoff. So this is where we'll pick this up. Any questions? Okay. All right. I'm going to move you over to the front of me, and let me stop my sharing here. There we go.